Good morning, everyone. I'm Viktoria, a space system engineer at EnduroSat. For those of you who don't know who EnduroSat is, we are a small satellite manufacturer. We design, build, and operate small satellites. We are based in Bulgaria, and we also have offices in Italy, Germany, and France. And today, I'm going to tell you about our most exciting and most challenging missions so far, the TOLIMAN mission. Toliman comes from the ancient Arabic name for Alpha Centauri, and as you might have guessed, the goal of the mission will be to observe Alpha Centauri from low Earth orbit. We're working on this mission together with the University of Sydney and sponsored by the Breakthrough Initiatives. The University of Sydney will be designing and developing the payload, which is a huge telescope, and we will be designing and developing the CubeSat. So you may be wondering, why TOLIMAN, why Alpha Centauri, and why using a CubeSat for such a complex mission? Well, there are several reasons. First of all, we want to find out if we are alone in the universe. And Alpha Centauri is actually the closest Sun-like star system. It's only 4.3 astronomical units away. So why not observe it? And we don't expect to find extraterrestrial life with this mission, but we expect to observe the habitable zone of these stars and to check if there are exoplanets orbiting these stars. If we prove that there are exoplanets, there will be future missions planned to find out if the planets are habitable and perhaps fly towards Alpha Centauri someday. Well, this is more in the long term. In the short term, we want to prove that our CubeSats are capable of performing complex missions, complex scientific missions. And we expect this mission to be a low-cost initial scientific assessment in order to open the doors for the next huge scientific missions that are available for CubeSats. And regarding the orbit, we will be launching in sun-synchronous low Earth orbit, a standard launch to maintain the mission as low cost as possible. During the initial orbital analysis, we found out that low inclination or ISS orbit will also be convenient for the mission. It will give us, however, less time during the year to observe Alpha Centauri, but more observational time per orbit. And with the sun synchronous, we'll be able to achieve more than 120 days per year of observations and around 26 to 30 minutes of observational time per orbit. And since Alpha Centauri is in the southern hemisphere and we will not be observing it throughout the entire year, there will be days during which we will not be observing Alpha Cent, but 61 Cygni, which is in the northern hemisphere. And in this way, we can actually check both stars. We will try for 61 Cygni because it's not that bright, but we will also try to gather some images from it. And regarding the orbit, during a single orbit, the spacecraft will have around 20 to 30 minutes for imaging, 10 minutes for downlink, and the rest of it will be idle mode with the solar panels pointed towards the sun so that the payload's aperture is pointing always away from the sun in order not to damage it. During the observational periods, we will have the telescope observing and collecting images and storing them in the payload computer where they will be processed. And just before downlink, those files will be transferred to the X-band transmitter. And when we establish, during the downlink session, when we establish a link with the ground station, we will be transferring those images with approximate speed of 125 megabits per second. Regarding the CubeSat architecture itself, it's a 16U CubeSat with approximate mass of 16 kilos. We will have eight units of those 16 dedicated to the payload. Most of the systems are designed by EnduroSat, the power system, data handling, communications. We'll be using our large battery packs rated at 84 watt hours of capacity. We'll be using the S-band transceiver, which can do 120 kilobits per second for TT&C. And for payload data, we'll be using the X-band transmitter, which is 125 megabits per second speed. And regarding the pointing accuracy, the spacecraft will have to be 10 arc seconds accurate, and we'll have to have a stability of 1 arc second per second. And these numbers may seem weird for a CubeSat, and indeed they are. They're also weird for us. This is one of our main challenges we're getting with this mission. And in order to overcome it, we will be developing a three-stage control algorithm for the ADCS, where the first stage will be using large reaction wheels to bring the accuracy down to 0.1 degrees. Then we'll have the second stage, which is fine pointing. It will use smaller reaction wheels to bring the stability down to 1 arc seconds per second. And the ultrafine pointing loop will use the telescope's high accuracy and include it in the control loop as an additional star tracker to achieve pointing accuracy of 10 arc seconds. And this is not the only challenge we're facing. The thermal system will also be very challenging because the payload needs to operate in almost constant environmental conditions each orbit. And this is around 20 degrees Celsius. To do this, we'll use a cold bias thermal system where the circumference of the payload will be covered with film type heaters to cover as most area as possible. And we will have temperature sensors and heaters, and whenever one of those sensors is detecting a temperature below a certain threshold, we will be turning on the heaters in this zone to balance out the temperature. We are still in the very initial design phase of this spacecraft, and those are the main challenges that we're facing. Of course, there will be more, but we are not aware of them yet. And we hope to overcome them easily in order to launch towards second half of next year and to achieve the goals of this paramount mission. Thank you for your attention, and I'll be glad to answer any questions.